Materials' properties, such as purity, impact their ability to be reused. An inventory of the waste properties has been performed for three important material flows: silicon kerf from sewing of wafers, silica from crucibles used in crystal pulling, and graphite from crystal growth furnaces. We will focus here on silicon. In the current state, around 35% is lost as silicon kerf is dispersed in the cutting fluid.
Utilizing the circular potential of these waste streams, 10 megatons of silicon could be unlocked by 2050 as secondary raw materials.
Typical particle size of silicon kerf is between 0.5 and 2.5 micrometer. The size of the particles depends strongly on the sewing process at a wafer producer and the used wire diameter.
Silicon particles having different size are agglomerated, and the morphology is ribbon-like and irregularly shaped.
Common doping elements used in silicon ingot production are boron, phosphorus and recently also gallium, which are again present in the silicon kerf. Additional dopant contamination sources for phosphorus are from the glue and beam materials used in wafer sewing.
Main metal impurities in silicon kerf are aluminum, iron and nickel. The main sources of metal impurities are the beam materials used in wafer sewing and the nickel-coated steel wire. The metal content in silicon kerf strongly depends on the beam material and the type of diamond wire used for wafer sewing.
Carbon and oxygen present the highest level of impurities in silicon kerf. Typical carbon concentrations are in the range of 2 to 4 weight%. Main contamination source of carbon is the cutting fluid used in wafer sewing. When the silicon kerf particles are immersed in the cutting fluid, they form an oxide layer from the reaction with water. Oxygen concentration are in the order of 4 to 5 weight%.
The oxide layer formed at the silicon kerf particle is around 1.5 nanometer.
The results obtained during our waste inventory reveal the contamination levels, composition and morphology of silicon kerf and provide insights relevant for subsequent processing and refining. For recycling it back into the PV value chain, silicon kerf requires different treatments: drying, cleaning, refining and agglomeration. The cutting process could be adapted to reduce and avoid the contamination by some impurities, which is currently investigated in this project.
If you want to learn more about the project, feel free to check our website and as well as our LinkedIn account.